Welcome, everyone. Thank you for joining today's WebGL and WebGPU Meetup. We have an exciting lineup featuring WebGL updates from the chair of the WebGL Working Group, Ken Russell, and WebGPU updates from Kelsey Gilbert, co-chair of the WebGPU Working Group at W3C. Following the updates, we will have presentations from Thomas Lucchini and Sebastien Vandenberghe from Microsoft on Babylon.js's WebGPU backend. Alexander Rose will present on adding illumination mode to Mole. Martin Valigursky from Snapchat will talk about PlayCanvas's render pass-based architecture. And Manuel Machado will show how Pixsplat utilizes WebGPU for accelerated performance. But first, a couple of housekeeping items. If you have any questions during the presentation, please ask them using the Q&A feature located on your Zoom toolbar at the bottom of your screen. We are recording this webinar and we'll share the link to the recording along with the slides on the event webpage. At the end of the session, please complete a short survey to help us better design future events. With that, I'll hand it off to Ken Russell, chair of the WebGL Working Group. Ken?
Okay, so hi everybody and welcome to the US Election Day version of the WebGL WebGPU webinar. Glad to have you here. Thanks all you dedicated graphics aficionados for joining. Okay, so Kelsey and I will kick off some updates, and here's our brief agenda. The WebGL section is very short, so I'll dive right in. So the first major update is on Angle's Metal backend. Work is still ongoing in this actively. There's contributions by Google, Apple, and independent folks. So there's been many fixes in recent months. Alexei Knyazov fixed a bunch of issues in texture projection, off and offset sampling, texture sampling with gradients for shadow samplers and on AMD GPUs. Apple colleagues fixed a bug with infinite recursion if you were using occlusion queries and had a lot of render passes underway. There were bugs in all sorts of stuff, clear colors with out of bound texture, etc. Won't drag you through all of it. But anyway, thank you very much to Alexei, Kimo, Dan Glastonbury, and Kuyen, who's the original author of Angle's Metal Backend, for all these great fixes. They're making the product across a range of operating systems more robust. And finally, on the WebGL side, there's been a lot of good progress in Pixel local storage. Work has resumed to finally ship this extension. There are simplifications to the underlying Angle specification and the implementation underway. And this, combined with a little bit of additional validation to catch stuff like rendering feedback loops, will actually complete this extension, and we're hoping to ship across all platforms in the next couple of months. So with that, let me hand off to Kelsey Gilbert from Mozilla to talk about WebGPU.
Thanks, Ken. This is our WebGPU update. We're still doing development on GitHub and at the W3C. If you haven't tuned in a bit, one of the main differences is now we're primarily working in the working group at the W3C instead of the community group as we work towards like actual publishing of specifications. After a recent face-to-face meeting last week, the API and WGL specifications are within one or two issues of being able to take our first candidate recommendation snapshot, which is maybe a boring spec-based thing, but it means it's almost at like a V1 release kind of thing. The main outstanding issues were around integer and stencil gather, portability, and stability. Have some questions we got to figure out there, but we're excited to give you all something awesome. We have a bunch of major progress about WGL texture operations in general, thanks to Greg Tavares from Google. The state of the art here is that things could be a lot more consistent across the board, and part of our guarantee for WebGPU is making sure that we give you something consistent so that you can rely on, and you're not trying to hunt down bugs on drivers. We're also working on subgroup operations quite a lot. That's one of the things we're really excited to get to a little bit more after we get our first candidate recommendation out there. But we're super excited about the capabilities and super excited to see what y'all are going to be able to do with that. We also did some brainstorming to figure out a roadmap for the next release now that we're finishing up this one, and put together a list of the topics that we think are most important to focus on next, so we can get you something high impact and super useful. Next slide. Our implementation status, not too much has changed here. So Safari is still enabled in Safari Technical Preview. Please test it. Please report issues. On the Firefox side, we do have an update. We actually are we have enabled WebGPU in nightly on Mac as well, so it joins Windows and Linux with having WebGPU available just on by default in nightly. It's not on in release yet. We're holding it back from release as we figure out the last bits for completing the implementation. But we're excited to have you give us feedback about the state of things as it exists in nightly, as we make sure that it satisfies your needs. And we're aiming to ship. We're pretty sure we're going to ship to release in early 2025, unfortunately, but that is a commitment from us, so we're working on it. Chromium currently shipping on Windows, Chrome OS, Mac, Android. Top of tree with the specifications. Please continue to give feedback. Like, it's released, but like, keep giving feedback. Like, our job fixing bugs sure never seems to be over. So we are really robust, but there's a lot of corner cases, and we're here to sort them out. That said, implementations, like when you write WebGPU code, they mostly just work. So just try them, just expect it to work. If it surprises you and doesn't work, let us know and we'll fix it. Next slide. So there's a bunch of work going on in 3JS's WebGPU backend, working to achieve parity with the WebGL backend and give people the confidence that they can just flip a switch and target WebGPU instead. There's been some hiccups on the API side. There's some restrictions that WebGPU has that maybe WebGL doesn't have. And they have some questions about whether WebGPU is stable enough. Obviously, we think it is. So we're going to work with them to figure out what question marks they still have. To ease developers' transitions, there's to WebGPU, there's still WebGL 2 fallback, and that's shipping everywhere, so like that'll just work. So you mostly don't have to worry. You can reap the benefits without eating the costs. It is a major architecture, but they're hopeful for major release later this year. And special thanks to Sunag, Mr. Dube, and Mugen87, and many others for driving this work. Follow 3JS for the team's latest updates. Next slide. Our samples, we're still excited about these. They're a little bit easier to participate in now, so we can add external samples too. So this is supposed to be a general thing. It's kind of official, but also like we want your input. Like, these are some of the things that not only are they for showing off what you can do, but within browsers and implementation teams, we do look at these, and these are some of the things we're like testing to make sure that they always work, things like that. So it's cool stuff. We're expecting them to work. If they don't work, either file an issue or find the issue. We already have filed about it because we think these are important. And submit yours. We'd love to have it. Show off something cool. Next. We still love these two resources. WebGPU Fundamentals by Greg Tavares and WebGPU Best Practices by Brandon Jones. They're really good. When people come to us and ask what we recommend, like, this is what we recommend. This is still what we recommend. Please take a look. Next slide. And contributions. Aside from the ways we already mentioned, please try give us feedback. Put together backends for your apps, like write new apps. Try out if you're using a framework, like try out the WebGPU version. Like, make sure it works before like early on, so we can make sure it works by the time you want to release it. Help us with conformance testing and contribute samples, demos, and articles for using WebGPU. With the community is really important to us, so we're really hoping that we can all build something really cool. Next. We have online communities, speaking of collaboration. On the WebGL side, we have the WebGL dev list. It's an email list. It's very general, so you can just ask things there. And honestly, if you're in the wrong place, we'll just like nicely let you know. But odds are we can get you an answer there. We also have a Crotus's public WebGL mailing list for more like questions on the specification side, but it's also available. There's a WebGL matrix chat room where browser implementers like me and Ken are just in there able to answer questions, and you can ask us things if you don't get your question answered at the end of the Q&A here. And as is usual, like there's lots of cool stuff on social media, so check that out. Next, please. On the WebGPU side, API feedback. There's a WebGPU GPU. It's still called GPU Web repository on GitHub. There is also a WebGPU matrix chat. Same thing there, and same thing with social media. We look forward to hearing from you all. And I think that's it. Thanks, Ken.
Thanks, Kelsey. Sorry, I fat fingered the last slide there.
No worries.
All right. So with that, Kendra, who's up next?
Thomas Lucchini and Sebastien.
So hello everybody, I'm Thomas from the Babylon.js team. I will also be joined by Sebastien in the Q&A part of the session at the end of all the different sessions. And wanted to start by looking back a little bit. We've been doing our first full WebGPU implementation back in 2022. It was pretty early, but we were shipping Babylon 5, so we had to make it very special. It was early, I believe it was not even origin trial at the time, so we kept following the evolution up until the summer when it was in our Chromium's versions of the browser. And what he was offering and what it is, of course, still offering today is compute shaders. You see here the nice ocean simulation that was supported by Alexi in our team that did most of the WebGPU implementation. But when they, because I didn't, but when they built this WebGPU implementation, what they had in mind was the backward compatibility. I think we're going to be for some time and maybe forever in a world where we have both WebGL and WebGPU. For sure now it's still early, and it was even earlier before. So it's very important to make it very easy for the developers, and the engine basically make it completely transparent. It's the same JavaScript code that works in WebGL, and if WebGPU is available, then it switches to WebGPU. Of course, you can change this behavior if you want, but that's completely transparent for you. This backward compatibility also brings sometimes some trade-offs in performance. So we added some special mode like the snapshot mode to maximize the usage of the render bundles. And in some cases, we'll see at the end, we can have very good increase in performance. So that's for the JavaScript code. In terms of the shader code, we of course, there is a lot of GLSL inside the engine itself, and then the custom shaders for the different developers. So for this, instead of rewriting everything, we are using GLSlang and Tint Wasm libraries that transcode and compile on the fly into WebGL. And if we look back a little bit, of course, there is another trade-off there. There is a time to download those libraries. There's a time to also transcode and compile. So for the V2 of the engine, the V2 of the WebGPU engine that is already there, we really took a native WebGL approach, and I'm going to go into a little bit more detail there. So some of the things are already released, and some will release in March. So first, the core engine, right? So the engine is made of TypeScript code and shader codes. And all the shader code was in GLSL, and now all these, hundreds, more than 200 shaders have been rewritten natively in WebGL. So it was tedious work, but it was, worth it to make the performance optimal. So if you're using out of the box the engine, you're 100% in WebGL. If you have custom shaders, of course, you can write them in WebGL and GLSL. But if you just want to stay with GLSL, then there is backward compatibility there. They are detected and compiled on the fly thanks to GLSlang and Tint Wasm. So that's for the core engine itself. If we look at, some of you may know Node Material Editor. So that's a visual tool that makes it easy for tech artists and developers to create different type of shaders. We started with material shaders, hence the name non-material editor. But now we can do much more. You can do post-process shaders, procedural textures, particles. Even Cedric and the team added Gaussian splat shaders, so you can apply a custom material to a Gaussian splat mesh, for instance, using a shader. So all this shader are written are the code for those shaders. So you assemble the nodes in a graph, and then the tool generates for you the shader, right? And it generates in GLSL. And now, again, we went behind every little nodes, and everything now generate also WGL, right? So natively, again, depending on what's the version of the engine that is running, then it will just be in WGL natively or in GLSL. And I'm going to do a quick demo here. That's why I share my screen. Here, so that's an example. So you have a node here. You have this fire material. This is not the right place. You have this fire material. So the way it works is you have input nodes like the time, the mesh position, and then you make all these transformations to output a vertex, the vertex output on one hand, and of course the fragment output there. So once you're done with this, you're pretty much done, right? We have now WebGL and WebGPU. So if I switch to WebGPU, so it's the same. Just the nodes are not expanded here, but it is exactly the same graph, of course. And you can export the shader if you want to see the code there. And that is WGL code. And if I go to WebGL, then I have again export shader, and then I have GLSL code. I was mentioning different type of shaders. You see here, that's a different type of shader we can do. So very very easy. I'm switched back to the slides here. That's another way to avoid writing two versions of a shader and maximize the performance, right? Because you have native, it's going to spit out natively WGL or GLSL. All right, moving on to something a little bit different. That is a huge endeavor in the team, which is building a new render graph based engine. So today, the rendering loop is like a block, right? Like a black box. Not completely. You can actually pass parameters and change a lot of things, right? But it's still a block. You have a main loop and a main rendering loop, and you can have secondary rendering loops. But the goal is to move to a completely new paradigm. This render graph-based engine where you have blocks and you can assemble them the way you want. And then the flexibility and the possibilities are limitless then, right? You can do pretty much everything, can optimize also everything. So that's something that is still in dev. The other two feature I just mentioned, the known material and the core engine are released, are available now. This one is still in dev. It's actually going to be a long journey. We did a long walk already. I believe Alexis just submitted the first major PR that kind of like lay down the first groundwork there. But there are a lot of work still to be done. Think of all the different features. A lot of features of the engine need to be exposed as blocks that can be combined there. So it's going to take some time. Probably it will not be for this Babylon 8 release, but it will be for the next release. But we'll do by increments. So as far as WebGPU, this render graph will support compute passes. So you'll be able to launch WebGPU compute shaders from within the render graph, which make it simpler to use compute shaders. It's more visual. You can easily understand your rendering loop and customize it, but also it will help optimizing the resource usage, like the storage buffer, for instance. So that's another big undertaking globally on the engine, but and in particular that will help for WebGPU. Moving on to the last topic there. Until now, I kind of shared some core updates on the engine and on the tool. This one is a little different, right? We wanted to make sure we can bring the benefit of WebGPU, of Babylon version of WebGPU, in a simple scenario, but very common, which is displaying a 3D model, a 3D scene on a web page. So for this, we took our Babylon viewer that was there and refreshed it completely. Adding dynamic loading for 3D formats. If it is a GLTF file, then looking at the GLTF extension that it's using and just loading those, just to optimize as much as possible the size. And this viewer is also fully extensible. So if you want to, there are things you don't like, you want to change and change some default parameters, you can of course change, and you can go very far because it's fully open. You can tap into the whole engine there. But as far as WebGPU, what it offers, it's a simple way to use WebGPU via a custom HTML tag. You have here the sample code of the viewer. Just say WebGPU, the file, and the environment, and there you go. You have your you can have your model displayed on the page. What is interesting, I was mentioning at the very beginning of this presentation, is that we created, when we implemented WebGPU in Babylon, we created the snapshot mode, and there are different levels, and here we put the fastest level of the snapshot mode, and that maximizes the use of render bundles. If you look at the right on the graph, on the picture, at the top you have a WebGL version that is running, and you see how everything is, a lot of things of course are being done on the CPU, and in the bottom you have the WebGPU version where a lot of the work, most of the work is now done in the GPU. It's not exactly the same scale, but just to give a visual hint there. This is actually the performance profile on my machine, which is on my laptop, which is kind of like pretty powerful for a laptop, I would say. So I had to we had to put a lot of meshes to see the difference. So there is, in this example, 25 by 25 by 25 meshes, so about 15K meshes. And I have an increase of about 50% more frame per second, right, between WebGL and WebGPU. So in complex models, it can really make a difference. The complex model on a powerful machine, but think of on a lower end device, then the threshold is much lower, right? So it could potentially help in a for lower end device, much more device, and much simpler models. All right, that is all for this presentation. That concludes it. You can ask any questions, and we'll be there with Sebastien at the end during the Q&A. Thank you all.
Thanks, Thomas. Thanks, Sebastien. Next up, we have Alexander Rose, who's going to be presenting on adding illumination mode to Mole.
All right, so yeah, my name is Alexander Rose. I'm one of the principal developers of Molestar. And Molestar is a larger suite of tools for handling molecular data on the web. So from life science, material science, wherever molecules and assemblies of molecules come into play. Big part of it is 3D visualization. We have a custom WebGL engine that scales from just a few atoms in a, let's say, drug molecule to billions of atoms in a cell. And here I want to talk a bit about how we added nicer lighting that works okay for all the use cases. So scales from a few atoms to whole cells. So essentially how we get from the image in the bottom left to the image in the bottom right, using some kind of path-traced screen space global illumination. Let's start with a few examples. So we can see in the examples here, we have on the left in the background, like a sort of whole cell made from a billion of atom and we can really see the sort of the scale and the depths and the crevices and all of that. And we can also have only emissive lighting. So you can, like in the top right, you can like have some drug molecule illuminate representation of a protein from the inside. Yeah, so the general idea was that we treat this SSGI mode as a progressive enhancement of sort, and try to reuse as many of the passes and code we use for normal rendering. And also to keep the overall look as similar as possible, so user can just switch from one to the other. So whenever there's a change in camera or geometry or lighting or so, we do a few passes. So we do a transparent geometry pass, because we don't do the SSGI for transparent objects yet. Then we have some post-processing input passes, outline. We have some transparent ambient occlusion. And then we have the input for the actual tracing. And part of that is also to get the depths of the back faces. Talk a bit more about later. And then, so that's sort of the input we do once there's any change. And then for the iterations of the tracing, we do like the sampling passes, and then we always do a composed pass that accumulates the samples and like adds some background to it, and some screen space anti-aliasing, boom, and depth of field, all of those things that can make it look nicer. And then, so for the actual tracing, so we have all the sort of the inputs. They're rendered by the same shader code. We just add 2 extra output targets, one with the normals plus like the emissive strengths for that pixel, and the plane diffuse plus like a value for like the visual density at that pixel. I'll talk a bit more about later. And yeah, we also have the front depths, and then we do a pass to get the back depths, back facing depths. And with that, we can do a sampling. It's a sort of very simple Monte Carlo, backwards Monte Carlo sampler. We only do it for diffuse, so the specular portion of it just comes from the shaded input color, just to keep it more simple and then faster. And then we do the standard Russian roulette to boost the non-terminated rays. And then for the tracing, so if you look on the right, for each pixel, we cast a ray, and that'll like either hit a background or it'll hit the surface, and then it can either hit nothing. Then we just return the shaded color, so the SSGI doesn't really do anything in that case. But if it hits another surface, then it accumulates the diffuse from there, and any emissive that may be there, and then just keeps on bouncing like a number of times depending on the parameter, and then yeah, it either hits nothing, so we can return the color, or it just gets, the ray just gets stuck, and we don't do anything with it. And yeah, so a few words about the thickness. So we need to somehow recover the thickness, so because it just lost in if we only have screen space information as input. And we want to make it as automatic as possible, so the user doesn't have to fiddle with parameters to make it look good. And the challenge there is that molecules are often represented. So the same data is represented with vastly different visual densities. So if you look in the top right, that's all the same data, but the visual density is vastly different. So the idea is that we just calculate a conservative base thickness from front and back face depth, and then we do a per object sort of scaling factor of the thickness to take into account that it's one of those visual representations with a specific density. So we can just set that as a default for each of these types of representation. And we still allow the user to tweak parameters, but hope they don't really need to do it. So there's an example on the bottom left there. If we just sort of take the infinite depthness, thickness, so basically just the front depth, then things are really overly dark. But if we have sort of this automatic thickness, we can get a sort of much more balanced look to it that has shadows where and darkening where you want it. And then, yeah, with that, a few notes on integrating this into the Molestar viewer. So we do a progressive rendering if the user enables it, like enables the SSGI mode to keep the viewport interactive. So of course we use request animation frame, but we also in WebGL 2 we check if the GPU is done rendering all the commands we send it, because we found that request animation frame sometimes fired even if the GPU was still busy, which wasn't what I expected, but you can get around with that. And then we also see how long a frame took, and then can adjust a few parameters to sort of scale from like a beefy desktop to a laptop. And then during the progressive rendering, we also adjust the denoise threshold to sort of hide this graininess. So on the right side, you can see if we don't do any denoising, it's very grainy. So we can do some sort of small scale Gaussian blur, but we want less blur once we have enough samples, so we just adjust that parameter. And then for screenshots, we want to take like as many samples as are needed to get a sort of converged image. And we found if we just do many samples in one go, the browsers don't seem to like that, and they just crash. So we again just submit it to the GPU in small chunks and wait in between, either using a fence, or in WebGL 1 we just brute force it by calling read pixels. And then for anti-aliasing, since we have sort of textures as input, we cannot just jitter the rays. We actually have to jitter the input as well. So we can do that every few iterations when we're sampling. And yeah, that's about it. So if you want to try it out, it's all open source, available online. If there are any questions, please ask them at the end. So thank you.
Thank you, Alexander. That's awesome. All right. Next up, we have Manuel Machado.
Hola a todos. Hello, everyone. My name is Manuel Machado. Today I brought you something a bit different from the most common 3D use case of WebGPU and WebGL. Not too technical heavy. Perhaps the idea of the presentation is showing something different than with this tech. In this case, WebGPU is going to be used for rendering and editing 2D textures, image documents. So let's talk about the product. Pixsplat is a powerful cross-platform web-based pixel graphics editor. There are many of these out there, but there is something special about this one, and that is WebGPU. It is GPU powered, and you can use it in your browser. The initial motivation for me to work on this was to implement a tool designed specifically for game developers, mainly because of the potential it ended up having. The scope increased, and now it is done so it's not limited to any specific type of artist. The main two things I think are the most attractive for both the user and me as a developer to work on this tool are one, the fact that it's web-based. For me, the web part is very important because I work with native desktop apps for years now, and it's never easy or quick to achieve any specific look and feel for the UI while also being cross-platform. So achieving this look and feel for this app would have been a nightmare without a web UI, which leads me to the second point. It is a web app that wants to compete with native apps and very powerful image editors out there. So how do I make it fast enough? And this is where WebGPU appears and shines the most. So let's talk about what I did with WebGPU. Pixsplat relies on compute shaders to perform any write or read operation on the textures. So for any stroke the user performs, there is a spot job that holds the settings of the brush and writes on them. And this works really fast, you will see, but that's not it. After the draw operation is done, I also need WebGPU to map the drawn area back to the CPU. This is done for two reasons. One, to provide the undo redo actions for the app, and two, to be able to restore the context in case of an emergency, a lost device, for example. So layers are basically represented by storage textures. We have a draw layer for every document, and that draw layer suffers read-write operations of the different brushes, which are triggered by different pointer events. When the event exits, an update of the composition of the layer will be submitted, and the next frame of the canvas will render something new. This happens all in GPU, so it runs quickly and it ends up being really responsive for the user, which is something very important for a drawing app. A little bit of code here. It is not exactly the code of the app, but the purpose is to show how the shader performs a read-write operation over a storage texture. This is 8 bits, but there is also support for 10, 12, and 16 per channel texture. One important note on this is not here, is that we have to consider that pointer events can go really fast and give us too many points to process in some cases. So it is not so trivial to handle them, so the compute job doesn't produce any unresponsiveness and works efficiently in general. Pixsplat takes care of this. In a way, it works fast and also prevents the GPU device from hanging in any case. Okay, so the drawing is done. I mentioned there is some logic to move back the information to the CPU. So every time an action ends, in this case, when the stroke ends, so-called affected region is calculated and a mapping from GPU to CPU over that region is performed. After that operation is completed, the buffers are updated and the data is ready to be saved to the state. Because of the mapping happening every time the user ends an action, this must be implemented in a way is non-noticeable, or at least it doesn't affect the user experience. So there is a complexity when handling big images because of the time and resources it takes to map all that information. For instance, if I have a huge image, there is no way you can allocate a buffer to copy it all at once because of the device limits. So you have to divide the copy in chunks. but always being careful with the resources of the user hardware. Pixsplat will not just create 200 buffers to copy every chunk of that image and submit all of them to the device timeline without freeing some in the middle. So the way this is done is you submit the essential work first, that is making a copy of the state of the texture you want to save, only the affected region, of course. And then after that, the user can keep doing whatever he needs with the main texture, and the app can submit and await all the times needed to make a smart usage of the device. All right, I got to explain the big picture of how this works. Let's see it in action for a minute. So this is Pixsplat. I will create the biggest image. It's not the biggest image possible, but the biggest preset here is 14K by almost 10K. This is a really big texture. No, I don't think anybody needs this, but for the purpose of the presentation, let's go for also a huge brush, like 2000 by 2000. Add a little bit of spacing because it's not necessary to have small spacing for this type of pixels, and then add some pen pressure just to show you how the pen tablet works. So if you press more, you have more opacity. All right. I want you to see how fast it responds. It is impressive if you are used to working with this type of software, because it usually starts being laggy and unresponsive with images this size and so many pixels run at the same time. We also have to consider that this is running on a browser, so the fact that it's able to compete in performance with native software makes it unique. Of course, you can transform these pixels just like any other image editor on there. Select, add text, draw shapes, erase, just like a regular image editor. All right, let's enough with the performance stuff. Let me show you something I prepared for you to show animations. I can show you all the features of animations, but I will show you my feature, my favorite feature, which is drawing while playing. Let's see if I can do this under pressure. I created a layer, I added a few frames, and I will just start playing. This is a preset brush that I created. And let's just start drawing. So while the animation is playing, this is drawing on the images. I feel like Bob Ross right now. Just happy little fire here. All right. Not too fancy. That's our animation. Of course, with time and patience, you can do much better than this. Let's export it. You can export this as, I don't know, a PNG. Of course, you can do a GIF with embedded animation, or just a strip that you can use in another program, like a game engine or something like that. All right, that's very nice. There's our fire. Right, let's go back to the presentation. Right, let's talk about future work. Because I have a lot to do. One priority to me is to wrap up the basic tool set for an image editor. Some basic tools like blur, the clone stamp, the finger tool are missing. Those are not really that complicated to implement. It would be amazing for a graphics designer to be able to quickly open Pixsplat on a tab or a desktop and edit an image without the need to open a big software that takes forever to load. After that, I want to focus on game development tools, because that was kind of the original scope of the product, and it is what I like. So that is like pixel art tools, color indexing, typeset utilities, and also better ways to work with 3D texturing without necessarily implementing anything 3D related yet. Just like special support for height maps, normal maps, specular maps, and finally go for the big fish, which for me is 3D asset texturing. At least starting with visualization would be amazing. I was taking a look at the GLTF compressor the other day, and having something like that, for example, integrated in a way that the artist can paint and edit the texture freely with the Pixsplat performance, but also see the final compressed result update automatically in the 3D model, could make this a powerful cross-platform tool for working with 3D assets targeted for the web. So all of this, of course, needs to be prioritized by feedback from the users, telling me what they need and what could be a good feature that can make their lives easier. That's why this software is already live, and you can use it as this is an alpha. The web version is completely free. So please give Pixsplat a try. You can access it at pixsplat.com, and if you would like to support me and the project, you can buy the desktop version that looks really, really good, by the way. And that's it. Short presentation. Thank you very much.
Sure, we could jump into a little bit of Q&A here. All right, so let's see. Why don't we start? Let's see, start at the top. And I see a question from Ellie Michelle. Hi, how heavy is tint WASM? I'm assuming that it is something that is shipped to clients whenever the Babylon view loads. Is it? And, maybe Thomas, would you like to answer this?
I can take this one, Ken, if you want.
Great, Sebastien. Yeah.
Sorry, guys.
Hello. So TintWasm is basically only downloading if you want to convert some GLSL into WGL. As with the next version, our next release, all the code has been rewritten in WGL. Normally, you don't even need it. It is around, it is quite big. It is around 2 meg. So normally what you prefer to do is to write your shaders in WGL and in GLSL for devices we don't support WebGPU. But it's a really good way to have a fallback without paying a lot of cost in dev time.
Okay, well, why don't we dive back into Q&A while we're waiting? Okay, so Ellie Michelle, nice to see we're getting closer and closer to a WebGPU release candidate. Will this apply to the C API as well? Kelsey, would you like to comment on this?
Sure, I can try. I don't follow the C candidate that well, except when they come to us with questions about it. I expect the C candidate will like track pretty closely to the specs. So I don't think you have any worries there. They don't have a standardization process that I know of, so I expect it to just work. And if it doesn't work, it's just a file an issue and we'll get it fixed for you.
Yeah, Ellie, maybe I can add just a little bit more color. So 2 colleagues are working actively on this, and there's a cross-browser, cross-organization little group working on finalizing that C header. There's still a bunch of smaller ergonomic changes that they wanted to make to the API, and they're plowing through getting those integrated, as well as implemented in at least one engine so they can be sure that they're going to work. And this is actively ongoing. I think they were hoping to have something within a couple of months that was considered like forward compatible. They weren't going to change it in breaking ways after that. So all progressing, and yeah, please do file any issues on the upstream WebGPU headers repository. Okay, so now Martin is back and we can see a really cool car. So Martin.
Amazing. All right, that's what you're supposed to see. All right, so as I said, we're gonna look at what PlayCanvas is, how we used to render before, how we're gonna render next, performance, and some demo. So PlayCanvas is 3D content creation platform, which basically consists of the editor where you can create a scene, set up lights, all that stuff. Then model viewer where you can publish your things, your GLBs or Gaussian splats, anything you want. We have Supersplat, which is splat editor. And you can publish all of that to desktop, mobile, XR, all the web stuff. And let's talk about what I need to talk about. So originally, the rendering was kind of like similar to other engines, black box, where everybody rendered same way. You would get some shadow maps rendered. Your scene would render using forward rendering. In the between, we can grab color or depth for some special effects later during transparent pass. And then at the end, there'll be loads of post-processing effects, and each of them would typically be a custom render pass, which means loads of memory access, reading and writing all over again. And final rendering often would go to multi-sampled frame buffer, which is again typically unnecessary. So we're spending a lot of memory bandwidth, especially on tiled surfaces or devices there. So the problems here we had, hard to customize. Like it was fixed rendering loop, and apart from post effects, that's what everybody was getting. As I mentioned, there was lots of multi-sampled buffers, which is really costly on mobiles especially. Many render passes for post-processing, which is again loads of memory bandwidth, reading it, writing, especially if some of them happen in multi-sampled way. And then code-wise, for us developers, it was complicated to maintain because it was all one big spaghetti code base where everything does happen together. So the plan was to go to render pass, as many other engines go this way these days. So render pass is a self-contained JavaScript module which helps us to write the code and understand it. It has clear interface, what is expected out of it, what are inputs, outputs, behaviors. Typically, render pass renders to render target, which could be multi-render target as well. Could be one or multiple color buffers, depth buffer, stencil buffer. And internally, the render pass can depend on other passes and can execute other passes. For example, the bloom can execute blur passes and similar. And each render pass under the hood stores information about what it needs to read and write specifically. For example, many render passes need to read the buffer and change it, but don't need to write it out because nothing needs it after that. So again, this is a way to save performance. So in the engine, we created whole heaps of these render passes. I'll go into details a bit later. And then on the camera, you attach a list of them, or typically just one with lots of dependencies. And that specifies the way the camera renders. Now, in the scene, you often have more than one camera, and the frame graph compiles a list of render passes out of all cameras. It basically creates a sequential list of them that we can send to GPU. So I'm going to look at a little example here where I have a scene with the chessboard and there's one light with HDR bloom. How we rendered this. So this render pass for the shadow, as you can see on the right side, and then we need to generate screen space ambient occlusion texture. That one requires prepass to generate depth buffer, and afterwards it runs the blur passes to blur the texture because it's kind of quite noisy. I'll show you later. So initially we regenerate shadow and the SSO texture, and the next pass is going to consume them and render the 3D scene itself. When 3D scene is done, we'll generate bloom texture out of it, and then compose pass at the end will combine the scene texture and the bloom texture to get the image you see there. So as I mentioned, all the render passes we have at the end create a single list. So this is the list for this case. And it's not particularly interesting to look at all of them, but performance-wise, the important bit is that only one of these passes renders to multi-sample texture, the scene pass. Everything before and everything after typically, for performance reasons, runs on single sample. That's a big performance win for us. The other important element we wanted to add to the engine is HDR rendering. Main goal was to improve quality of rendering and have physically based bloom instead of the old 8-bit bloom we used to have before. So under the hood, we render to multiple formats that have more than 8 bits per channel and fall back to 8-bit if that's not available. Then all scene rendering and post-processing uses these formats, so all the data throughout the pipeline is stored in HDR format. then at the end, it depends what we output to. We can output to the typical ADR, LDR screen, which is just 8-bit. And in that case, the final compose pass will apply tone mapping to bring the values back to the 0-1 range, do gamma correction. But we can also output to HDR display, like your Mac displays and many other screens these days. And WebGPU gives us option to output to RGBA 16F texture. So we use this if the user enables it. Then the bloom, fairly typical implementation of physically based bloom. First, we render the scene into HDR buffer, and then we need to apply a large blur to it to spread out the highlights. We use progressive downsampling and upsampling, which is multi-render pass, but is a lot cheaper than large kernel blur for the same quality. So as you see on the left side, we have the blur texture that's generated, and on the right is the blur texture composed on top of the scene. Then another pass, as I mentioned, is SSAO. We generate that in screen space as typical, and it's based on the depth buffer. Depending on number of samples you use, the image is quite noisy. So as I mentioned before, we apply a blur, depth-aware blur filters to get rid of the noise, and we end up with very convincing self-shadowing kind of image that is consumed either during the rendering for the better quality or during the final composition as just overlay on top. Okay, the other bit we've done is the TAA, temporal anti-aliasing, and that's the alternative to multi-sampling. Basically, it's like a super sampling, but it happens over many frames instead of paying the cost every frame. So the solution here is fairly straightforward, similar to many other papers online. Camera jitters, subpixel every frame, and the frames are accumulated over time. We handle the moving camera by depth reprojection, so we know where the camera or the pixel was the previous frame, handle this occlusion using color clamping. And as you know, TAA tends to add a little bit of blurriness, so we add sharpening on top to kind of compensate for this. So far, we only handle moving camera, even though this solution seems to handle the moving objects reasonably well, but we'd like to improve it and use the motion vectors to handle that. That's to do. And then at the end, when we have all these textures evaluated, scene rendered in texture, we have a compose pass. It combines all these textures that we generated and applies many other effects, like sharpening, color fringing, color grading, vignette. If we output to LDR, it's going to apply tone mapping and gamma correction as well. And as I said, typically we either output 8-bit or 16-bit, depending on the screen that you have on your device. Quite often, actually, during the rendering scene like that, there's UI that renders at the end as well, or after all post-processing. So we render it on top using separate render paths. But as they all render to the same render target, we simply merge them together to save the bandwidth. So we only write it out one time with UI as well. So another optimization there. Now, so all this technology is written and has been released in the engine for a few months now, even though we're improving it. And now we're integrating that in the editor. So as you can see, these are the controls that currently are exposed on the camera. We can play and set up your scene the way you want to. Fairly easy to use. Performance. Now, I was testing on 4K screen, Apple M1 Max, with bloom, SSAO, color grading, and vignette, old versus new. And the improvement is massive, even though the quality is better in the new system now that we have HDR and proper bloom and everything. So most of the cost is due to the fill rate savings, not having too many render passes that read and write out of memory on mobile and desktop as well. Future. So we'd like to release this to the editor, which is very soon, a couple of weeks, hopefully. We're just in the testing phases. And then keep adding new techniques as SSR, depth of field, auto exposure, distortion, integrated optimally for our users so they can easily access that without having to write loads of render passes themselves. As I mentioned, for TAA, we'd like to improve the motion vectors for dynamic scenes and optimize a lot of it. Lots of these examples are already out in our GitHub account, so have a look, please. And this is the example inside the editor, which is going to be released fairly soon. Not sure what the quality is with the compression, but it's pretty awesome. It's got TAA enabled as well. So I'm going to shortly enable and disable it, so before and after, so you see what difference this makes. Now I'm going to turn off the SSAO specifically and play with some bloom parameters. So yeah, we're very excited to ship it out soon. And that's it. Thanks for listening.
Bravo, Martin, and I guess Will and the PlayCanvas folks. This is just really, really beautiful. All right, awesome. So why don't we jump back into Q&A? I'm sure that the audience already has a bunch of questions for folks, and I think maybe even some of the presenters have questions for other presenters. So diving back in, Ellie Michelle also asks, in Pixsplat, how do you handle fast-paced stroke events technically? This is for Manuel. If there are 100 events within the same frame, do you treat them all at once, one by chunks, etc.?
That's actually a really good question. So the pipeline receives a point list, not a single point. For each coordinate dispatched, I need to know how heavy the brush is at that point. And I necessarily have to iterate over those points that I receive to get that value. There is no way around that iteration because the brush can be anything. Even a random texture where the alpha level does not depend on the distance to the center of that brush. So the problems to solve here is that the user can trigger more pointer events than we can handle. Also, remember the browser can coalesce many points into a single event. If for any reason the browser has to merge many pointer events, you will end up submitting more work than the device can finish in a reasonable amount of time. Sorry, I have my camera off. Hello. So the dispatch events must be throttled because one, we know the CPU works better with smaller and simpler tasks in general, and two, even without considering that, if you read the spec, there is a denial of service section that is pretty clear about this. You can't cause unresponsiveness for too long. I tried it. If you do that, you will lose the device. So the way this is done is, well, a QE logic. You put the points into a QE, and as soon as the pipeline is ready to receive more points, you dispatch them. But be careful. The point list cannot be too long, but it can't be too short either, because it is also to consider the amount of time it takes to set up the path encoder and submitting it. So it has to be something in the middle, because you will end up taking too much time from the CPU otherwise. I hope that answers the question.
All right, awesome stuff. Very, very clever batching. And actually, Ellie has a follow-up question right now. Do you use the Ink API? It's linked here in the Q&A. But
yeah, no, I don't use that. Not at all.
Yeah. All right, very, very cool. Let's see. Going on to the next one, Emil Bogomolov asks regarding Pixsplat. Once again, Manuel, you're the man of the hour. Is there any feature that can add a pixel art specific look to a drawing that I've made? Like, could you draw a regular fireplace and then get it in pixel art style?
I can do some quantization, but I do that to export the GIFs because the color indexing is needed for exporting GIFs, but I do that on the backend that is in the native app only. But I'm planning to do those kind of things for sure on the web version too. And that would be actually there is a tutorial on the WebGPU fundamentals page about generating a histogram And you need that actually for one of the algorithms. I believe it's a Chinese name. I don't know the algorithm name right now, top of my mind, but there is an algorithm that needs the histogram, and then you can quantify the image. I hope that's the question. There is no option to do that right now, but it will be. And I'm looking forward to techniques to do that, of course.
All right, very nice. So the last queued up question right now we have from an anonymous attendee, and I'm pretty sure that none of us can answer it, but the question is, I joined late, so not sure if this was answered already. It wasn't. But is it true that WebGPU is enabled by default in the upcoming iOS 18.2 that is shipping in December? Kelsey, do you want to say anything to this?
Sure. I wish I knew too. Apple keeps things pretty close to the chest, and this is no exception. I have no idea, and that's not just a bit. I actually have no idea. So hopefully is all I could say, but like I literally don't know. And no one who knows will be able to tell you, unfortunately. But hopefully we'll find out.
Even if an Apple employee were here, they would say that they don't pre-announce products. So what I can suggest to all folks that are here, and tell your friends to, please test with Safari Technology Preview on an ongoing basis. You test your WebGPU content with it and file bugs on bugs.webkit.org if you run into any issues. That's the best way to make sure that your stuff is going to work if they just turn it on. Hopefully, if there was a showstopper bug that you discovered in tech preview, they'll backport the fix to Safari stable before they ship it. Okay. We have another question for Manuel in the queue. Let me, in the interest of fairness, let me jump to some of the other questions that we had for some of the other presenters. So look, Martin, let me target one to you. Is your render path solution supported on all platforms and devices?
So this is coming to PlayCanvas engine version 2, which is WebGL 2 and WebGPU. We dropped WebGL 1 from here. So it's supported everywhere there, with the exception of small number of devices where float render targets are not available. So for these, we're gonna drop some, for example, HDR Bloom, but otherwise it runs across WebGL 2 and WebGPU.
Okay, and let me see. Oops. I think we have a question for Alexander. Yeah. So Alexander, do you think that compute shaders could improve the efficiency of your Illumination algorithm? And like, if so, can you think of how maybe data structures might change if you were using compute instead of iteration and fragment shaders?
Yeah, I haven't thought about that too much. I've seen some people struggling with getting more performance out for post-processing algorithms when moving from sort of WebGL to WebGPU using compute shaders. So probably will require careful tuning of work groups and that sort of stuff. But yeah, I haven't really started looking into that.
Okay, well, we'll also work on adding ray tracing to the WebGPU API, and that'll solve everybody's problems.
Well, I mean, it will not just magically work with a billion entities then, so we still need some solution for that. So probably something hybrid.
Right, very good
where
point.
You do some screen space stuff and the rest, and yeah. But I mean, with compute shaders, you definitely have much more options.
All right, all good. Let's ask one more question of the Babylon.js folks. Would you say, like Thomas and Sebastien, that most of the core shaders in the engine are written using the node material editor at this point, or do you have like GLSL and WGSL versions of most of the core shaders?
No, so the non-material editor is to write your custom shaders, right? And so it's for a specific type of shaders, material, procedural, Gaussian splat, some Gaussian splat things, particle shaders, but all the core engine shaders have been written by hand in WebGL and in GLSL.
All right, very cool. Let's see. There's another question about Pixsplat. So Manuel, gotcha up here. In
Yes.
Pixsplat, when you're drawing into a running animation, what are the limits regarding texture size and frame count, and are multiple layers supported in this?
There are no limits that, well, of course, your GPU has to support it. The more memory you have, the better. There's actually no way to know how much memory you have, but I implemented a memory tracker. I manually track the textures you have loaded and the buffers as much as I can. And that you provide that limit manually by default. I think it's 3 gigabytes. I have to define that better, but you can increase that. If your CPU can handle it, then there's no problems. Of course, you cannot draw a video 30 FPS HD. You will have an issue there, but if you have the limit well set up, Pixsplat will let you know that you cannot create more textures because you will crash your device. If you swap documents, the textures are released, but within the same document, everything you have set up, it is loaded into memory. So you have to consider that.
Yeah. A GPU with a lot of video memory.
Mm-hmm.
Okay, let's see. So the person who asked the previous question about iOS 18.2 sent in a link to Unity's discussion forum where Brendan Duncan, who's the lead engineer on Unity's WebGPU backend, talked about his experiments with iOS 18.2. So anybody who is interested in that, I don't know quite how to share this link with all the attendees, but maybe we can post it later. Let's see. So I wonder whether it's okay to dive into some of the questions that were asked that seem to have been retracted, but there's one interesting one here. So Emil asked for the Babylon.js folks, is the graph solution going to be an alternative to writing JavaScript code to produce an animation from scratch?
Let me take this one, Thomas. So basically, the code we are writing now with render graph is not meant to create animation per se. It's more a way to define with a node-based kind of architecture the way you want to render your frame. So it will help you designing all the different passes and so on that you want. Currently in Babylon, we are more like having all the passes within our scene, which are defined, and it's kind of case by case basis. If you've got some bloom, we are just knowing we need to do the bloom pass and so on and so forth, and we are doing everything automatically, but it works until one point where you want to customize it and add more into it or remove from it for performance reasons. And it's why we are now building a way to allow the users to completely customize their render pipeline within Babylon. So we are going one step further than what we were having with post processes. So we were able to attach before post processes to the camera or render pipeline to the camera. Now users can create their own pipeline through a visual tool, which was previously pretty kind of heavy in terms of code that you needed to do and requires changing in the scene and so on.
All right, cool. Looking forward to more flexible, rendering with less code.
And really optimized as well. Yeah.
Good, good. There's another one that we had in the queue. This is from Martin from PlayCanvas. How can I add custom render passes to my render pass-based rendering?
So I guess if you want to use custom render passes, there are two ways. You can completely take over and just write your passes and attach them on the camera, and it'll render whatever you need. The other option is you can use the render pass that we have, the default one with most of the effects integrated. You can extend that class, that module, and override some functions. For example, the one that puts or registers render passes. So you can add your render passes in between the one that we provide. So there are these two ways, I guess. Take over or extend what we have and add your stuff or replace stuff.
All right, very
Thanks.
cool. All right, I think we may have gotten through most of the questions here. Does anybody else want to drive or? Oh, we got a new one in. Okay, great. So Miguel Iranzo asks, now that WebGPU's been around for a bit more, what direction do you expect the future of graphics on the web to go, especially having mobile devices on mind and the performance limitations that developers are limited by? Kelsey, would you like to take a first crack?
Oh, goodness. That's a broad question. I expect that we will continue to iterate on WebGPU for some time. I don't expect there to be like a WebGPU 2, the same way that we like have a WebGL 2. I think it's gonna be more of an iterative thing, where we add features add optional features as we find things that we think are valuable, and also try to bring things into core as we figure out how to offer things on older devices, and also as older devices kind of age out and we no longer have to support them and can increase the limits that we guarantee to everyone. That's, I think, the main things we have in mind. Specifically for mobile devices, we have some things that we're hoping to help with performance there in the future. Trying to figure out things like UMA, subgroups will probably help a bunch, and other optimizations, tile storage stuff. There's things that we can still add to WebGPU for some time to like keep moving things forward. And so that's where I expect to go for a while still.
Sounds great. Great answer. All right, let's see. Do any of the panelists have any questions or comments for other panelists or about their presentations?
I have a question. Can I ask?
Please.
On WebGPU, we can currently output or request frame buffer to be 16-bit float. And I've seen some presentations for the same on WebGL, but I could not get this to work. What is the state of this?
So we've been working on expanding out the set of formats that you can select for the drawing buffer. There's a new drawing buffer storage API that I think is actually implemented in multiple browsers at this point. That is the thing that gets you beyond what the core WebGL API provided. It's really a matter of integration in order to basically support HDR for WebGL, and then getting that into the core APIs to make it make sense. Right now, obviously, you have to render to your own render buffer or texture and then blitz the screen in order to get that kind of stuff on the screen. And the question is whether you want to select, extended range rendering on a device that's capable of it, like you can in WebGPU, and then put the stuff out. So it's a small matter of programming, and I think most of us are focused on the WebGPU solution because that's more forward-looking, and then we'll backport the results of WebGL. But Kelsey, do you have any further comments?
Yeah, concretely, I'm pretty sure drawing buffer storage is the thing for WebGL, and I think Chrome implements it. I don't know about all the details because there's a bunch of like, does it support it on this configuration? What does it support it in software rendering? I don't know. In Firefox, I'm hoping to have support in for that pretty soon. It's actually one of the patch queues that is on my list right now that's about to go into review. So I'm excited to get that out here. So that'll be in before end of year, but that's all I can say right now. It's definitely, for the most part, for the vast majority of users, if you can do your rendering on whatever back buffer you want, and then if you don't have drawing buffer storage support, just do the mapping yourself to the SDR output and it'll still be pretty good. But for true like HDR rendering, like that takes drawing buffer storage in WebGL, and hopefully that'll be supported everywhere sometime by 2025, hopefully.
Sounds good. Yeah, thank you.
I would also have a question.
Please.
Yeah, so I found it very hard to figure out how powerful a GPU is on a device that I'm currently sort of running code in. And that makes it very hard to scale something like screen space GI from like a mobile device to a big powerful desktop GPU. Yeah, so I guess
Yeah, it's a hard one.
yeah, so I mean you can try to measure the frame time, but then you need the disjoint timer query, and that's very restricted, and it's also can be quite noisy. You can try to parse the GPU device string, but that's also for fingerprinting reasons, I guess, not available everywhere, and you would need to constantly update that. So I don't know, from a developer perspective, it would also be helpful to at least have some sort of notion of how powerful the GPU is, just a few classes. So yeah, so we can like, because the alternative is to give the user like a drop down where they can pick the settings what they want. But would be good to at least be able to have a reasonable default for such a setting, and then if the browsers could offer some qualified estimate of how powerful the GPU is, that would be great.
Yeah, we have talked about in this past. We still kind of feel that like the option of just like having the user pick is like kind of the best one, honestly. Start them out on something reasonable, dial it back if you can't make the frame rate, stuff like that. Giving you more than that, it's just a really hard quantification problem. It'll depend a lot on your like the details of what you're doing. It's good to hear that there's still a desire for it, so we can like take another stab at brainstorming. But like I'm not super optimistic that we can get something that's that useful.
If you do have ideas, please feel free to file issues on the GPU Web/GPU Web repository. I think that would be the best place for something like this, as opposed to thinking about it in the context of WebGL. But I mean, think about the dimensions. Like you've got really powerful desktop tiled GPUs nowadays with Apple Silicon, but you know, a lot of the other discrete desktop GPUs are immediate mode, you know, full frame buffer, like NVIDIA's and AMD's. You know, there are GPUs out there that have really high compute bandwidth, but low main memory bandwidth, or relatively low. And you can still do some pretty sophisticated, say, compute shader algorithms on them. So it's been really, really difficult to quantify what is the performance tier. So if you have ideas on like one way to express this, we're all ears. Okay, well, actually, we are running up against the hour-and-a-half mark, so I think we should say thank you to all the presenters, and thank you, everybody, for attending. This was great. Yes, thank you for attending, and thank you, Kronos, for organizing. Really appreciate it.
Yeah, thank you so much, Ken, and thank you again to all of our presenters for these wonderful presentations. As a reminder, a recording of this presentation along with the slides will be available on the Kronos website, and we will send you a direct link in a follow-up email within a day or two. As you leave the webinar, please take a moment to fill out the survey that pops up. Your feedback's important to help us improve these presentations, and let us know if there's other Kronos-related topics you'd be interested in. Thanks again for joining us, and hope everyone has a great day.